wherever. So, 6.3, frequency and impulse response. We're building up these really interesting mathematical objects, and in this lecture we're actually going to complete our map that we have of all of our different representations of systems, all of our different mathematical models. We're going to have the last one today. So that's kind of sad, but that means we've covered all of the common system representations. So it's pretty sweet. So proceeds in two parts. First, the Fourier transform is used to derive the frequency response function. And actually, I forgot to update this because I had changed this. And then I use it to derive instead of the steady state sinusoidal response, which I will do, but not right now. Why is that? We're going to instead find the frequency response, and then we're going to find the impulse response. So I'll explain why as we go. So first, frequency response functions. This is the last of the ways we'll represent systems mathematically. So consider a dynamic system described by the input-output differential equation with variable y representing the output, dependent variable time t, variable u representing the input, constant coefficients a, b, order n, and m less than n, for n being a positive integer. We have this, right? Which is just a fancy way of writing any order linear input-output ordinary differential equation, which we know how to solve. We know how to change it into a transfer function. We know how to find it from state space model. We've seen it a lot of times, right? Could be first order, second order. We started learning how to solve these in our differential equations class. Okay, so we learned about the Fourier transform last time. We're going to use it. So we take the Fourier transform of equation 619 to yield something interesting, assuming zero initial conditions. So do you guys remember when we took the Fourier or the Laplace transform of both sides of this equation to find the transfer function? Remember that? Those are good times, right? This is what we're gonna do here too, but we're gonna use the Fourier transform. Okay? So Fourier transform of the left-hand side, Fourier transform of the right-hand side have to be equal to each other. Then what I do is Fourier transform is just an integral, right? So you can integrate over each term separately, and of course constants can come outside of the integral, so we can do that. And we're left with all of these Fourier transforms of time derivatives of the output y and time derivatives of the input u on the other side. So now is a good time to switch over to our handy Fourier transform identity table from Appendix C3. We can look on the left column for functions of time, and the corresponding Fourier transform is on the right column. And then alternatively, you can go from the right-hand column to the left-hand column. That would be the inverse Fourier transform. So just like your Laplace transform table, we have a Fourier transform table, right? So time derivatives show up right here, right? It says that the nth time derivative of some function of time is just j omega raised to the nth power times the Fourier transform of the function. So just like with, remember there was one very similar to this with the Laplace transform, right? Except for it was s to the n instead of j omega to the n. Okay, so let's apply that. And we have our j omega to the n plus the constant is still there, j omega to the n minus 1. So all of these times, the Fourier transform of the output y, which we will write with a capital Y. And similarly on the other side, the input u is written with a capital letter to denote that it is the Fourier transform of that letter, of that function. So now we can algebraically solve for y and get the following. Y equals b m j omega to the m plus bm minus 1 j omega to the m minus 1 plus down to b1 times just j omega plus b0. And in the denominator, we have j omega to the n plus a sub n minus 1 j omega to the n minus 1 plus a1 j omega plus a0.
The last term in the numerator plus b naught, is that what it is?
Yeah, exactly. So this is very familiar. It looks a lot. Oh, what are we missing here? U, right? So this should be U. Okay. So we've solved for y, our output, the Fourier transform of our output, right? So the inverse Fourier transform, which is denoted with script f to the minus 1, of y is the forced response. So just like with the Laplace transform, we can solve the differential equation this way. However, this is not our primary concern. Rather, we're interested to solve for the frequency response function h of j omega as the ratio of the output transform y to the input transform u, i.e. y over u. And we use this strange way of putting j in the argument here, okay? So I'll talk a little bit about that in a moment. But let's say, okay, h of j omega is equal to y over u. So all you need to do in this equation is divide both sides by u, and we're left with 620b, which is our typical form of our frequency response function. So we use this, so strictly speaking, h is a function of omega, okay? And some people will just write like that. A lot of engineers write the j in there. And it's mathematically not great, but we do that, and I'll explain why by looking at this next step here. So note that our frequency response function can be converted to a transfer function via the substitution j omega goes to s, and conversely, a transfer function can be converted to a frequency response function via the substitution s goes to j omega. So, as in h of j omega equals the transfer function h of s evaluated at s equals j omega. And this is why we'll write h of j omega. It's like h of s, we just stuck the j omega in there for s. So it's a strange notation. It's kind of awkward, but it works. And that's what you're going to see a lot of times in the engineering literature is the j omega in there. So it's just good to get used to it. It's often easiest to first derive a transfer function using any of the methods described previously, then convert this to a frequency response function. So we typically don't go through this Fourier transform definition to get to it. Usually we'll find the transfer function, and then we'll just stick s equals j omega in the transfer function. Okay. Now, what are the ways we know to derive the transfer function?
The impedance method?
Impedance method. Yes, impedance method. That was the latest one we learned, right? That was like the most direct. And what did we do before that?
State space.
So yeah, we used the state space model conversion to the transfer function. Yeah. And then there's also finding an input-output differential equation and then taking the Laplace transform too. So you can do that way too. So we have a lot of ways to find the transfer function. We're just going to say, since they're so close, we might as well just find the transfer function and just plug in s equals j omega. Okay. Now, we're going to use this. And there's some really interesting things that we can find out about this frequency response function. We're going to use it quite a bit. It's a really powerful tool. I would say it is on par with the power of the transfer function. I mean, it's just like really, really powerful for us. So for the last, so we have this week, we have after spring break 2 more weeks, we're going to spend pretty much working on things to do with the frequency response function. So it's like right where it's at for us. So from above, we can solve for the output response, y, from the frequency response function by taking the inverse Fourier transform, right? So y of t is equal to, by definition, the inverse Fourier transform of y, which is by definition the Fourier transform of y. So the inverse Fourier transform of the Fourier transform of y is y, okay? Why? Just because.
Why not?
From the definition of the frequency response function, which is 620a, so this one here, y over u, we can just plug in that y is equal to hu, right? So we need to take the inverse Fourier transform of the frequency response function multiplied by u of j omega, which u of j omega here, we're just saying that's the Fourier transform of the input, okay? The convolution theorem, which you can look up, states that for 2 functions of time, h and u, f of h convolved with u, which I'll talk about convolution in a second, is equal to the Fourier transform of h times the Fourier transform of u in the time domain, which is to say h u in the Fourier transform domain, where the convolution operator star is defined by this function here. So 624 is the definition of the convolution operator. So h convolved with u is defined as being this integral. So convolution is something that it's confusing to a lot of people. I think it's because of the way that it's introduced. It's just this. This is the definition of it. It has a lot of interesting properties, and it gives us access to a lot of system dynamics analysis. And one of the things that we try to do with it is to sort of give you an intuitive understanding of it, but I feel like that's actually a disservice because it kind of confuses people. So 624 is just the definition. If you're going to convolve 2 things in the time domain, you just have to integrate them. But what the convolution theorem states is that if you're going to convolve them in the time domain, that's the same in the frequency domain as just multiplying them together. So if they're convolved, h and u are convolved in the time domain, they're just multiplied in the frequency domain. And the converse is true also, but we typically are convolving in the time domain. So that's convenient because we get hu showing up right here, right? hu in our solution. And so, therefore, our y of t, which is what we're after here, is just equal to, of course, I'll rewrite this. So it's the inverse Fourier transform of h of j omega u of j omega. So if we look at this, though, if we take the inverse Fourier transform of this side, we take the inverse Fourier transform of this side, and we're just left with h convolved with u, right? So that means that this right-hand side of our expression down here is just h convolved with u, which is just by definition, so 624, by definition, h convolved with u is the integral from minus infinity to positive infinity of h of tau u of t minus tau d tau. Okay, so this is the solution, right? I mean, everything's expressed in the time domain. You have to do an integral, right? You have to integrate this function. But this is the solution to, it's the forced response, but it's the forced response of the system. So we call it the frequency response in terms of all time domain functions. So we've solved it. So we've solved this for any input. You put in any input, and you have to put in, h is a weird thing. What is little h? What does that mean? It's the inverse Fourier transform of the frequency response function, right? So the Fourier transform of the frequency, the Fourier transform, which is the frequency response function, h of j omega, it needs to be inverse Fourier transform to get to the time domain, right? If you got to the time domain, it would be little h. So we've never even found a little h before, but I mean, it's a thing, right? It's the inverse Fourier transform of the frequency response function. Now, it's also something else. It happens to be something else. By definition, it's just the inverse Fourier transform of the frequency response function. But there's another interpretation of it, and we'll derive that here. And it's important as well. So the frequency response result includes an interesting object, h of t. What is the physical significance of h, other than its definition as the inverse Fourier transform of h of j omega? Consider the singularity input u equals delta of t, an impulse. So remember our Dirac delta impulse function that we put into a system sometimes and we see a response? It's just like, represents like a sudden spike in the input, right? So I know what happens, that's why I'm putting it in. If you didn't know beforehand, you wouldn't know to do this, but it works out nicely, so we'll do this. So we'll put it in and we'll see what happens. Frequency response is just plugging it into this solution here. Y of t is equal to the integral of h of tau delta of t minus tau d tau. Now, the Dirac delta function, remember it's not strictly a function, it's actually defined in this integral sense, and it's called a distribution. We often will pretend like it's a function though, and it behaves mostly like a function most of the time. But one of its primary properties, probably actually its definitive property, is that if you have it inside of an integral like this, it has this property called the sifting property that gives you, as a result, the function that delta is multiplied by, which in this case is h, evaluated at this argument, t. Okay? So it gives you h of t. The sifting property says, oh, okay, wherever delta is effective, wherever that peak occurs, is what it takes for the value of that function. Okay, so it sifts out h and evaluates it at time t. Now, that might seem a little weird, but if you look it up, the sifting property literally says 6.25 is equal to 6.26. That's like literally the sifting property. And it shows up a lot. And in the next lecture, it'll show up again in another derivation. So it happens to come up constantly. And a lot of people have had didn't like this Dirac delta function. It was actually invented to go along with quantum mechanics. And people, even like really famous physics geniuses like von Neumann took exception to it. They didn't like it at all. They felt like it was this sort of fiction, and it wasn't until somebody really went and defined it not as a function but as a distribution that people became okay with it. But it's a really interesting object. So I mean, you guys are working with something right now that like is at the heart of quantum mechanics. So you're welcome. I don't know. Congratulations. So, but when you guys read through, because I know you guys will get curious about quantum mechanics at some point, you read through some quantum mechanics stuff, these distributions and these delta functions show up a lot. So anyways, pretty fun stuff. Okay, so the sifting property is really a useful property for us in these derivations. So y is just equal to h of t. That is, so another interpretation of 626 is that h is the impulse response. Okay, so it's the function of time that results in the output if you put in an impulse to the system. If you whack it with a hammer, h of t response is the response. A very interesting aspect of this result is that h of j omega is equal to the Fourier transform of h. That is, this is by definition, right? The Fourier transform of the impulse response is the frequency response function. A way to estimate via measurement the frequency response function, and therefore transfer function of a system, is to input an impulse, measure and fit the response, then Fourier transform it. Of course, putting in an actual impulse and fitting the response perfectly are impossible. However, estimates using approximates remain useful. Approximations would be better. It is worth noting that frequency response and transfer function estimation is a significant topic of study, and many techniques exist. Another method is described in the next lecture, too. So we're going to learn another way to do this in the next lecture. And this is, so when you guys are starting to think about, okay, when am I going to use the system dynamic stuff? When am I going to use, like, the impulse response? Like, not that interesting, right? It seems really theoretical. But when you have a system that's relatively complicated, and it's hard to break it down into its parts and analyze it, okay? Coming up with a nice theoretical transfer function for it to describe how it works. A lot of times you're stuck with just estimating its transfer function by measuring it. So that's a really good way to go, because you don't have to get all of your, like, you don't have to say, oh, this is a mass and this is like a spring, or like, and this has inductance associated with it. You just simply put in something and you measure something, and then you estimate how the system's going to respond as a transfer function. So it's a nice sort of very practical thing to be able to do, measuring the transfer function, estimating the transfer function. And this is one of the ways, and it's kind of weird, right? Like, why would you expect that when you walk up to something and you whack it with a hammer, why would measuring the time response from that have all the information in it to tell you how it responds? Remember, the frequency response function tells you how it's going to respond at all frequencies. It's kind of weird, right? I mean, you didn't even put in a sinusoid at all. Like, you just put in a sharp spike. And here's a little bit of something to help you to understand why this works. So we go back to our table, and we find our Dirac delta function, our impulse, in the left-hand column. And we follow it over, look at what the Fourier transform is. It's 1. Okay, so what does that mean? If you looked at this, if you look at the spectrum of it, so if you looked at what I will call h of j omega, so where this is omega, for this delta input, h of j omega, if you graphed it as a spectrum, it's just a flat line of height 1, right? Now, this says that this Dirac delta function, this impulse, has the same frequency component at all frequencies. It has some component at all frequencies, right? Of course, that's actually not, you can't instantiate that in an actual impulse. It would have to be infinitely short in duration, which is impossible to do, but you can approximate it, right? So we can't really elicit all response from all of the frequencies. But the idea is that we are exciting all of the different frequencies of the system and seeing the response from all of them at the same time in the impulse response. And that's why when you take the Fourier transform of it, you see the response of the system. So, yeah. Okay. I probably shouldn't have called it H. Probably should have called it U, because that would be our input, right? We're putting delta into the function as the input, so yeah. H would be a poor choice. Okay. Any questions on this? That's all I had for you today. Question?
Oh, that was it.
Oh, I see. Okay, cool.